Welcome back, all of you. I will begin with Unit 3 in this video lecture, and we'll begin with the very important topic, that is phase log loop. Uh, Phase log loop is a very, you can say, important device or circuit. It's typically used to track the phase and the frequency of the carrier component of the incoming signal. This usually the major application of PLL is to track the frequency and phase of the incoming signal. Mostly the carrier signal to have its application in the demodulation process. So it is therefore a very useful device for synchronous demodulation. It's a very important device for synchronous demodulation of different modulated signals, amplitude modulated signals, where we suppress the carrier. So for those modulated signals, we require the synchronous type of detection, synchronous type of demodulation, wherein we need to generate a local generated carrier signal whose phase and frequency are exactly synchronized with the phase and frequency of the carrier signal used at the transmitting end. So it is therefore a very useful device in the demodulation process. It can also be used for demodulation of the angle modulated signals. It can be useful for the amplitude modulated as well as angle modulated signal, where the conditions of low SNR ratio is there. It is really helpful in the demodulation of such signal. And another important application, one is synchronous demodulation. Another important application of the phase log loop is the clock recovery system. Clock recovery systems. That is again very important for the synchronization purpose, which includes the timing recovery in digital receiver. So we can say that this PLL circuit plays a very important role in the analog as well as the digital communication. It is helpful for synchronous type of detection in case of analog communication systems, and it is helpful for making a clock recovery system or timing recovery system in the digital receiver. So we can say it plays a very critical role in both modern digital as well as analog communication system. You can say it plays a very critical role in both analog and digital communication systems. Any PLL circuit has three basic components. So if you look at the basic components of a PLL circuit, there are three basic components. The first one is your voltage control. The first one is a very important component, that is a voltage controlled oscillator. VCO. Second one is a multiplier or a phase detector, or you can say a phase comparator, phase detector, or it's basically a multiplier circuit which acts as a phase detector or a phase comparator. And the third one is a loop filter with some impulse response, let's say H of S. So if we draw the basic block diagram of PLL consisting of these three blocks, it's kind of a feedback loop. I'll just draw the basic diagram of PLL. This is the multiplier, or you can say the phase detector, followed by a loop filter, and in the feedback loop we have a VCO. So if we label this block diagram, this is your multiplier, and the input signal is, let's say, A sine omega ct plus theta it, and the signal coming out the VCO is, let's say, we assume the signal to be 2 of P cos omega ct plus theta naught t. And let's say this is the error signal E naught. This is the basic block diagram for a PLL circuit, which consists of three important things, three important blocks. Which is one is the multiplier. This is the multiplier which acts as a phase detector. Then we have a loop filter, which is usually a low pass filter, and then we have a voltage controlled oscillator, which is present in the feedback loop to change the output signal accordingly as we give the input to this DC. Okay. Now, with the help of this the basic block diagram, let us understand the PLL operation. So let us look at the basic PLL operation based on this block diagram. The operation of PLL, it is, you can say, quite similar to the feedback system. So you must be familiar with the feedback system. In the case of typical feedback system, the feedback signal tends to follow the input signal. That's the scenario. Okay. So if the feedback signal is not equal to the input signal, the difference, or you can say the error, will change the feedback signal until it is very close to the input signal. So if we take any typical feedback signal system, let's say this is the feedback system we have. So let's say this is the input signal input, and this is the output of this feedback loop. So the function of this feedback system is to bring this two signals, input and the output, similar. Okay. So initially, if there is some error between these two signals, that error is given as input to the feedback system, and then the function of this feedback is to minimize this error so that the input and the output are very close to each other. So a similar kind of operation is followed by the PLL. It follows exactly the function of a feedback loop. The only difference in case of the PLL is that it does not bring back the amplitude, rather it brings back the phase equal to the phase of the input signal. It tries to lock the phase of the input and the output signal. So the PLL tries to lock the phase. PLL tries to lock the phase instead of the amplitude. This is the major differentiating point between a PLL and a feedback system. Okay. So in case of PLL, the VCO adjusts its own frequency such that the frequency and the phase interact the phase and frequency of the input signal. So the VCO adjusts its own frequency, such that the frequency and phase of can track the input signal. So this VCO, depending on the given input, it changes the frequency of the output signal so that the frequency and phase of this input signal is being tracked. Okay. Now we can clearly understand the working principle here, that how the frequency and phase of the signal are related. So let's say if we have a sinusoidal signal, okay, and if we plot it on a phase plane, let's say we mark 2 points on the sinusoidal signal, and the corresponding 2 points on the phase plane are these two. So let's say this is the phase difference theta. Okay. Now this sinusoidal signal has a particular frequency. So these 2 points will rotate with a particular speed. These 2 points will move with a particular speed on this signal, right? Because the frequency is fixed. So obviously this point and both the points are moving with the same frequency or the same speed on this signal. So this difference will remain constant, right? So here we can make a very important conclusion that signals having a constant frequency will have a signal having the same frequency will have a constant phase difference. Signal having same frequencies will have constant phase difference. So this phase difference theta will remain same as these two points move on this signal, and the vice versa is also true. It's a very important conclusion, and its vice versa is also true. It's a very, very important conclusion, and the PLL, working of PLL is broadly based on this principle. So let us analyze this working block by block. Let us analyze the VCO part. So VCO, voltage controlled oscillator, is the oscillator whose frequency can be linearly controlled by the input voltage. You know that VCO is an oscillator whose frequency can be linearly controlled. It will linearly controlled by the input voltage. Okay, this is how we can define a voltage controlled oscillator. Now let us see the working of it. So if a voltage, if a VCO input voltage is, let's say, E0 t, this E0 t is the input voltage to VCO as shown in the this diagram. This E0 t is the input voltage to the VCO, and its output is a sinusoid with instantaneous frequency given by, this is the instantaneous frequency of the output of VCO. So omega t is equal to omega c plus c into E0 t. This is the instantaneous frequency of the VCO output. Instantaneous frequency of VCO output. Okay, where C is the constant of the VCO, C is the constant of VCO, and omega C is a very important parameter, which is the free running frequency. Is a free running frequency of the VCO. So it's the frequency of the VCO when error is 0. When the error is 0, omega t will be equal to omega c, which is, that means the instantaneous frequency of VCO is nothing but the free running frequency when there is no error. That means both signals have been synchronized or locked. Okay. Now, if we look at the block diagram of this PLL, the two incoming signals, one is this incoming signal and another one is the output of the VCO, are getting multiplied so that we can detect the phase difference or the phase error between the two. So we are next multiplying these two using the multiplier. So next our component is a multiplier which multiplies the two incoming signals, and the multiplied output is further followed by the loop filter, which is then further applied as input to the VCO. This is the overall structure of the PLL block diagram. Okay. So the VCO output, we know it is B times cos omega ct plus theta naught t. VCO output is nothing but B cos omega ct plus theta naught t. And then its instantaneous frequency is, it is omega c plus theta naught dot t, where theta naught dot t is equal to c into E naught t. Okay, you know this relationship, and where this c and b are the constant parameters of the PLL, and we know the incoming signal is your A sine omega ct plus theta it. This is the incoming signal, input signal to PLL. Okay. So if this is the incoming signal, and when we multiply these two, the multiplier output, let us analyze the multiplier output now. Multiplier output will be equal to A into B sine omega ct plus theta I into cos omega ct plus theta naught, right? If we further simplify this output, AP by 2 and this sine theta I minus theta naught plus sine 2 omega ct plus theta I plus theta naught. So this is the simplified form of the multiplied output. Now this multiplied output is passed through a loop filter, which is basically your low pass filter, right? So this low pass filter, what it will do is it will block the higher frequency component. It will eliminate this part of the signal, and hence the effective output of this loop filter is what? 1 by 2 into AB sine theta IT minus theta naught t. This is the effective output of this loop filter, and this is nothing but your the error signal E naught t, right? Now let us further analyze the working of this loop filter. Let's say if ht is the impulse response of the filter. Let's say if the ht is the impulse response of this filter, so we can say that this E naught t is nothing but ht convolution with 1 by 2 AB sine theta IT minus theta naught t. Okay, so just make a small correction. This is not E naught t, rather E naught t will be the output of the loop filter. So if the impulse response of the loop filter is this ht, so E naught t will be ht convolution the multiplier output, which is ht convolution the multiplier output. If we simplify this convolution operator, we get half AB integration 0 to t h t minus x sine of theta I x minus theta naught x dx. We have just simplified the convolution operator, nothing else. Let us label this equation as equation A, and we already know that this theta dot is equal to C into E naught t. Just name this equation as B, which is the change in the frequency of the VCU. Okay, we've already seen previously this. Yeah, this theta dot naught t is equal to C into E naught t, which is nothing but the change in the free running frequency. Okay, so let us substitute A in B. A in B. So substitute this theta dot naught t is equal to AK, and also let's substitute K as equal to 1 by 2 into C into B. We can make this substitution because all the quantities are constant in this. So this theta naught t will be equal to AK integral 0 to t h t minus x sine of theta E x dx. Okay. The theta E is the phase error. So theta E here is nothing but the phase error, and that is equal to theta IT minus theta naught t. Theta IT is the phase of the incoming signal, and theta naught t is the phase of the output of the VCU signal. This is nothing but the effective phase error. So now if we carefully analyze these two equations, let's say equation C, equation D. So these equations immediately suggest a new and a more elaborative model of PLL, which is that is we have you can say a summary. We have input phase theta I, and other phase input is theta naught t. Okay, and the output is theta. This is plus, this is minus. Theta E, error in the phase. We pass it through a sine function, and the output is your sine theta e t, and then we pass it through a filter providing the gain a k into h of s, and the output will be your theta naught dot, that is c into error function, which is given as input to a integral from 0 to t. So if we carefully analyze this equation number c, then we can make more elaborative loop diagram for PLL, which is shown over here. It is nothing but a diagram, a description of equation C. You can correlate equation C with this diagram further. And now with the help of this loop filter, we'll find out the error analysis of the PLL, how we can find out the error and things here. Before that, if you just look at this loop, you'll get to know the overall purpose of PLL. Okay. See, the input signals to this first block are theta IT and theta naught t, which are the two different phases of two different signals. And the purpose is to minimize the difference between these two and fix that distance to be that constant value. Okay. Even if there is some change in this phase, this feedback loop will function in such a way that again the phase difference will be minimized and it remains constant immediately. So this summation, this generates a error, phase error we can say, which is passed through a sine function, and this sine function multiplied with this constant to generate this theta dot naught function, which is c times e naught t, where e naught t is the error. Now this error is given as input to the VCO, or you can say this integral over here to generate theta naught. So the overall purpose or the function over here is to minimize the error between the two phases, the two incoming phases. Now let us have a look at the small error PLL analysis. Small error PLL analysis. So in case of small error PLL analysis, we assume that there's a very small phase error, that is, so we can have a valid assumption in that case that sine of theta is approximately equal to theta. It's a very small phase error. We can have this valid assumption. And now if we look at that block diagram, this block diagram for equation number C, we can say that it is reduced to the linear system, which is if we apply this assumption, this block diagram can be reduced to this is the error, phase error. So this overall this loop diagram, if we apply this valid assumption, it's limited to this integral. If we apply it in the S domain, it's nothing but equal to 1 upon S. Ht gets converted to h of s, right? So this is equivalent to a linear system. Linear system that is equivalent to theta I is the input, theta I is the output, and k h s divided by s plus k h s is the loop pulse response theta naught s to the output. Let us analyze this mathematically as well. So now this output theta naught s divided by theta I s will be equal to ak hs by s 1 plus ak hs by s. And it will be equal to a hs by s plus the same, right? Therefore we can say that PLL acts as a filter with this transfer function. You can say that the PLL acts as a filter with this transfer function.